Now the next is the superheated vapor. So far we have discussed how to read thermodynamic properties from saturated table. If the state of the substance is saturated liquid, saturated vapor, or anywhere in within this dome or in the mixture region. Now there are tables available for this region, which is superheated vapor, and also there are tables available for this region, which is compressed liquid or subcooled liquid region. So this region, which is the to the right of that saturated vapor line, and here the temperature is, at a temperature above this critical temperature, all this region is actually a region in which a substance will be in superheated vapor form. So in this region, temperature and pressure are independent properties. Here, within this region, both temperature and pressure were dependent, because for every temperature there was one fixed pressure. But here, once you are in this region or in this region, now temperature and pressure are independent properties. They are not dependent upon each other, because for this pressure line, this is TV diagram, so this line represents the pressure line. So there is a possibility exists of uh, many temperature lines would be crossing this pressure line. All these are various temperature lines, but within this dome, only one particular temperature line and this pressure was coinciding with this pressure. So within the dome, both temperature and pressure were dependent upon each other. But once we are in this region, which is liquid region, here again, for the same pressure line, a number of different possibilities of temperature lines may exist. So all these temperature lines are actually intersecting this pressure line in the liquid region, and all these temperature lines are intersecting the same pressure line in superheated region. But within the dome, for this pressure there was one fixed temperature, and we can find out this temperature for this pressure from the saturated pressure table, right? So now we shall learn how to read the thermodynamic properties for this region, which is superheated region. Then we shall discuss about the compressed liquid region, because now we have already covered the saturated liquid and saturated vapor lines or saturated properties on these lines, saturated vapor line, or on this line, which is saturated liquid line, or anywhere within this dome. So now we shall learn about the superheated region. So I have explained these 2 points. Now the superheated vapor table is different from the saturated vapor table. In saturated vapor table, you saw there was VF, VG, UF, UG, HF, HG. But here you have only V, only U, only H, or only entropy S, because in this region, for any particular temperature and pressure, there is one fixed V. Right? But here, for one particular temperature and pressure, there were two V's. One was VF, the other was VG, or HF, HG, UF, UG. But here, for any fixed point, this one, or any one, or which is intersecting on this pressure line. So for any particular temperature and pressure, there is one fixed value of U, V, and H. So there is no more UF, UG, VF, VG, or HF, HG. So now how to read this table, how this table has been constructed. So I will explain it now here. So you can see in this table, there are a number of temperature data is given, and for one fixed pressure. There is another pressure, and again a number of temperature values are given. And what are these temperatures? Look at this line. Let me erase it, clearly explain. Okay, so now you can see, for example, the pressure is 0.5 megapascal. So this line represents, for example, the 0.5 megapascal line. So for this 0.5 megapascal line, what is this temperature? This temperature is the saturation temperature for this pressure, and that temperature is 151.83 degrees Celsius. So on these superheated vapor tables, you will see for every pressure in the bracket there is a temperature written, and that temperature represents this temperature, saturation temperature, right? And the first row on these superheated tables gives the VUH values for a saturated point. So it means, and which saturated point? For this saturated, not this one. This is saturated liquid, this is saturated vapor, because superheated region is starting from this point onwards. From this point onwards, it is all superheated. So this first row is actually telling us the values of V, specific volume, internal energy, enthalpy at this point for this pressure, and for this saturation temperature, which is 151.83 for this pressure. This again data is for water, right? So this first row is actually the saturated vapor properties, right? And the next is the temperature higher than saturation temperature. For example, this temperature is 151. So this is 151. So 200 will be somewhere here. So next value is, for example, for 200 degrees Celsius. This line represents 200 degrees Celsius, and this temperature line is intersecting this pressure line here in the superheated region. For this point, here is the V, U, and H values, and so on. For higher temperature, 250 degrees Celsius. This two, for example, this line represents 250 degrees Celsius on TV diagram. So this will be intersecting this pressure line somewhere here in the superheated region. So that's how this superheated table is constructed. Now you can notice that there are no values below this saturated point, because below this saturation temperature of 151, this temperature line, for example, this is 100 degrees Celsius line. This line will never intersect this pressure line in the superheated region. This line, this temperature line, which is lower than saturation temperature, that is 151 degrees Celsius, it is intersecting this pressure line in the liquid region. ये इस liquid region में इसको intersect कर रही है. So it means that is liquid region, that is not a superheated vapor, that is subcooled or compressed liquid region. For this point, we need to see the table of compressed liquid or subcooled liquid region, right? So that's how the properties are shown or tabulated for superheated region. So let's see another example. What is this? 0.1 megapascal. So it means if this line represents 0.5 megapascal, so it means somewhere below this line, for example, is 0.1 megapascal. 0.1 megapascal. So as the pressure is reduced, so the saturation temperature will also reduce. So what is this saturation temperature? That is 99.61. So it means this line is actually 99.61 degrees Celsius for this pressure. And what is this first row of this table? That is for 99.61 degrees at this point, saturated vapor point. From this point onwards, it's all superheated. So you can read the data values directly from this table. And then for 100, higher than this, this is, for example, 100 degrees Celsius. Now it is intersecting here. Then 150, this one. So now all these temperature lines are intersecting the same pressure line, 0.1 megapascal, in superheated region. But this temperature line, which is lower than 99, it is not intersecting this pressure line in superheated region. This line is intersecting this pressure line in the liquid region. So you have to consult the liquid region data or subcooled liquid data to find its properties V, U, and H. So that is about the superheated liquid, superheated vapor region, thermodynamic properties of superheated vapor region. That's how those are represented. So you will see at the end of your book such tables for superheated region. So for every pressure, there is a set of temperature starting from saturation to some higher value till 1300 degrees Celsius. For example, data is given, is tabulated, the experimental data. So that's how you can read the superheated vapor table. So the superheated table has certain properties. So whatever we have discussed, now this will be shown in terms of number of characteristics. So we can characterize superheated vapor compared to saturated vapor. So let me explain it with the help of this figure. So the characteristics of superheated vapor are the number one is low pressure. P is less than P sat at a given T. Now let's try to understand this point. P is less than P sat at a given T. So at a given T, for example, this is some given T. This is a constant temperature line on PV diagram. Now what is it saying? At a given T, pressure is less than P sat. It means for this temperature line, what is the saturation pressure? So for this temperature line, this will be a saturation pressure line, right? And for the same temperature, a number of pressure lines will be intersecting this temperature line. All these are pressure lines in the superheated region which are intersecting this temperature line, and all these pressures are lower than this pressure. What was this pressure? This was P sat for this temperature, and all these pressure lines are also intersecting the same pressure, but where? In the superheated region. For example, this pressure line, this is a higher pressure, higher than T sat. This pressure line is not intersecting this temperature line in the superheated region, right? So it means for a superheated region, all these points are superheated region. P, this pressure is always greater than, sorry, P sat is always, this P sat pressure, saturation pressure is always greater than these pressures. P sat is always greater than P. All these pressure lines are lower than P sat. All these pressure lines are lower than P sat at a given T. So for a given T, there is one fixed P sat, and all these pressure lines which are intersecting this temperature line, they are lower than P sat. That is the meaning of this point. So it means you can say that superheated vapor, the condition of a substance will be a superheated vapor if pressure is lower than P sat. All these are superheated points, and all these pressures are lower than P sat for that given T. That's how you interpret. So second characteristic of superheated vapor is that temperature is greater than T sat. So at all these points, because it is in superheated region, so this temperature must be higher than P sat at a given P. So let me show it for a given P. Now I will explain the second characteristic. What this says, at a given P, so for example, this is given P. At a given P, all these points, all these temperature lines are in superheated region. All these temperature lines are, and all these temperatures are greater than, what is this temperature? This is T sat. So this one is T sat. So for a substance to be superheated, all these temperatures must be greater than Tsat at a given P. At a given P, this is a given P. And what about these temperature lines? These temperature lines are lower than Tsat. They are lower than Tsat. That's why they are intersecting this pressure line in the subcooled liquid region. So that is the characteristic of subcooled liquid region. But what is the characteristic of a superheated vapor region? For a superheated vapor, the temperature, all these temperatures are greater than Tsat at a given P. Right. This is the second characteristic. Third characteristic, all these volumes at a given P and P. For example, you are given a temperature. This is a temperature and this is a pressure. So now this intersection gives this point. And at this point, at this given pressure and temperature, this V is greater than Vg. This V is greater than corresponding Vg at a given P and P. Right? Or in other words, at a given P. Or explain in a different way. Now what is it saying? V is greater than Vg in superheated region at a given P or T. At a given P and at a given P. For example, this is given P. This V is greater than corresponding Vg. Right. At a given P or at a given P. At a given P, this point has a higher volume than Vg. At a given P and at a given temperature, this V is again greater than this Vg at this temperature. So that is the meaning of this third point. Similarly, the same you can say about internal energy. Internal energy U is always greater than Ug, and similarly H is greater than Hg, because everything as we move from liquid towards gaseous region, V, U and H are all increasing. So that's why V will be greater than Vg at a given P, or it is or, not and, or P at a given P or at a given P. This volume or internal energy or enthalpy will be greater than the corresponding Ug, Hg or Vg. Similarly, this point will be greater than the corresponding Ug, Vg and Hg at a given P or at a given T. So these are the characteristics of a superheated vapor. Right. So now we have learned about the saturated properties, how to read saturated properties, saturated liquid, saturated vapor, and how to calculate the thermodynamic properties within the dome or in this mixture region. And now we have also studied how to read the thermodynamic property table for superheated vapor region. Now one region is remaining, and that is compressed liquid, this region. So this whole region which represents compressed liquid region. So now we shall learn how the properties can be evaluated for compressed liquid region. So for compressed liquid region, there is one important thing. So for example, this is the dome on same temperature versus volume diagram. So on temperature versus volume diagram, this is, for example, a pressure line. So this is pressure line. These are pressure lines in liquid region, and we can notice one thing, that all these pressure lines are very close to each other in the compressed liquid region, and they are diverging from each other in the superheated region. So that's why in case of liquid region, for example, if you are at this point or at this point, now what is the difference between these 2 points? The temperature. Pressure wise, pressure lines are very close to each other, but temperature effect is quite significant. So if you are on this point or on this point, same temperature, but pressure lines are so close that these 2 points will be very near to each other, because these pressure lines are very close to each other in the liquid or compressed liquid region, not like in the superheated region. So compressed liquid properties, they are mainly dependent upon temperature much more strongly than they do on pressure, because pressure lines are very close to each other in the subcooled or compressed liquid region. So that's why, and the effect of pressure is so negligible that even if you increase the pressure by 100 times, this will not change the thermodynamic properties in the compressed liquid region up to 1%, right? So that will cause the properties to change less than 1% if we increase the pressure by 100 times. I redraw it again to clarify this point. For example, these are the pressure lines. They are so close that, for example, this is the pressure, this is a pressure, and if you increase this pressure by 100 times, so this change in V, change in V, specific volume is on x-axis, this change is less than 1%. Here I have shown it afar apart only to explain that there are different pressure lines, but they are so close that this change in volume by changing the pressure by 100 times, because as we move from this point till this point, pressure is increasing. If you increase this pressure by 100 times, the change in thermodynamic property, for example volume, is less than 1%. That is the meaning of that sentence. Right? So it means when the effect of pressure is negligible, so what we can do, I draw it again here. So for example, this is TV diagram, and on this TV diagram, that is the curve, this is the pressure line, sorry, it is separate, another pressure line. So for example, we are here, this is a certain pressure P, certain temperature T, and we want to find out this volume V, right? So here we can use one assumption. If you have a separate table of compressed liquid region, you can calculate this volume directly from that table, and that table will be very similar to a superheated vapor table, that for a given temperature and pressure combination we can find out V, U and H. So these compressed liquid region tables are very similar to superheated vapor table, right? But here, because the effect of pressure is so negligible, so we can say this, at this point the volume can be taken as equivalent to this point, because this distance is negligibly small, because these pressure lines at this particular temperature, the effect of pressure in the compressed liquid region is so negligible that we can assume that this V is nearly equal to this VF. What is this point? VF at this temperature. So you cannot neglect the effect of temperature, but you can neglect the effect of pressure, because from this point till this point pressure is changed, but the effect of pressure in the subcooled region is so negligible that we can say at this temperature volume here or internal energy here or enthalpy here can be taken equivalent to corresponding HF, UF or VF at that temperature. We are neglecting the effect of pressure. So that is one assumption which we can use for compressed liquid region, right? So that is written here. So any thermodynamic property in compressed liquid region can be assumed to be YF saturated liquid value at that temperature. The effect of pressure can be neglected only for compressed liquid region. So for compressed liquid region, you can find out all these thermodynamic properties from the saturated table. In that saturated table, only the saturated liquid values can be used at that temperature. So the effect of temperature cannot be neglected. If, for example, temperature is this one, and here is this pressure at the same pressure, but you can assume this point to be here. So now you can find out V at this point at that temperature from saturated liquid table or saturated properties table. So at this point V can be assumed to be Vf at that temperature. Again, the effect of pressure is neglected, but the effect of temperature is not neglected. So that is one assumption which we can use in compressed liquid region. So we do not need to go to compressed liquid table to find out these properties. We can also use that assumption. Right. Okay, so that is the assumption that any thermodynamic property can be assumed equivalent to a corresponding thermodynamic property at saturated liquid at that temperature. This Y could be specific volume, internal energy, or enthalpy. Right. So compressed liquid may be approximated as a saturated liquid at a given temperature. For example, given P and T, we can take V as Vf at that T, U as Uf at that T, H as Hf at that T, and the effective pressure is negligible. In all these thermodynamic properties, enthalpy is one property which has more strong dependence on P, because H is given by U plus PV. So in case of H, we may have more error if we are using this assumption, because H also accounts for the effect of pressure in it. It's not just U, because U is only dependent upon temperature, but H is also dependent upon, has some dependence on pressure also. So therefore for H we can modify the same equation as this one. So H is not simply Hf at that T. We can say that H is equal to Hft plus this V into P minus P set. That effect, because that effect of pressure, because we are, for example, this point is at which we want to find out enthalpy, and we are assuming this point to be here on saturated liquid state, but from this point till this point there is a change in pressure, and that change in pressure is accounted for. So we can use this equation to find out enthalpy, but in most cases we can simply say H is nearly equal to H of T. But for low to moderate pressures, from very low pressures to some moderate pressures in this region, we can use this equation for more accurate value of enthalpy. Right, but even this will not yield any significant improvement at moderate to high pressures. So if the pressures are very high, for example, you are in this region, then even this modification may give large errors, and then you may have to consult the correct value from the compressed liquid region table. Right, so for low to moderate pressures we can use this assumption or this assumption for enthalpy, but for high pressure regions, for enthalpy we should not use this or this assumption. Then we have to consult the actual thermodynamic property table of compressed liquid region. Right, so compressed, just like superheated region, we can also characterize compressed liquid region. So let me explain those properties here again with the help of that diagram. So what is the first property? Higher pressures. P is greater than P set at a given P. For superheated vapor, it was P was less than P set at a given T. So now let's again, I explain it again on PV diagram. So this is temperature versus volume diagram. On this diagram, this is, for example, dome, and here is one temperature at a given T. So for example, that is a given T. At some T temperature line. So this is the pressure line. What is this pressure? For this T, that is the saturation pressure. Right. And there are a number of pressure lines which will be intersecting this temperature line in the subcooled region. Now all these pressures are actually greater than Psat. All these pressures are greater than Psat at a given T. That is the meaning of this thing. And you may say all these pressure lines are not intersecting this temperature line in the superheated region. They are intersecting only in the compressed liquid region. So that is the property of a compressed liquid region. Second is at a given P. Now I show it here again. So I show it again. So now what is it saying? At a given P, for example, this is given P, some constant pressure line. T is less than Psat. So in the subcooled liquid region, this is the temperature for this given P, this is Psat. And all these temperature lines which are intersecting this pressure line in the subcooled region, all these temperatures are lower than this Tsat. This is Tsat, this is Tsat, and all these temperature lines which are intersecting this pressure line, they are in the subcooled or compressed liquid region. So that is the second. So the reverse was true for superheated region. T was greater than Tsat at a given P. P was less than Psat at a given. Similarly here, volumes, for example, this is the point in compressed liquid region. So now at this temperature and pressure, this specific volume is less than Vf, corresponding Vf at that temperature, or at that pressure, this is Vf. So this value is less than both of these. So at a given P or at a given P, volume of that compressed liquid is less than the corresponding Vf. Right. Similarly, U is less than Uf, H is less than Hf at a given P or T. The same which we have learned in the superheated region. In the superheated region, V was greater than Vg at a given P or T. But here V is less than Vf and V is definitely less than Vg at a given P or T. And similarly, U in the compressed liquid region is less than Uf, although this difference will be very small for liquid region, liquid to saturated vapor, but definitely it is a little smaller than the Uf at a given P or T. Similarly, H is less than Hf at a given P or T. So I hope it is clear. If it is not clear, so I will repeat this concept in the on-campus class, face-to-face class, because I know it's difficult to communicate in the online lecture. So we can have a repetition of these concepts, brief repetition in the campus, on campus or face-to-face class. So now we shall solve a numerical problem to understand all those concepts, right?